Welcome to the deep dive. Today we're looking into astrometry. Now, on the surface, it's about measuring positions, motions, stars, planets, that sort of thing.
Right. Celestial objects.
But when you dig a little deeper, it turns out there's this, well, incredibly long and really impactful history behind it.
Absolutely. It's fundamental.
So, our mission today, for you listening, is to figure out why measuring these tiny, tiny angles of stars has been so crucial for our whole picture of the universe and why it still matters.
Yeah, and we'll be tracing that journey, drawing on sources that cover everything from, ancient skywatchers right up to the latest space mission.
Quite a span. Historical context meets cutting-edge measurement tech.
Exactly. And the core idea, the thing that links it all, is this quest for precision in measuring where things are up there. How that seemingly simple act changed everything.
Okay, so let's jump way back to the beginning. We're talking over 2,000 years ago.
Oh, easily. The roots are incredibly deep. For a huge chunk of history, astronomy was astrometry. They weren't really separate things.
Just watching and measuring.
Pretty much.
Yeah.
And the sources point way back, even before 2000 BCE, to the Sumerians in Babylonia.
Oh, okay.
They're the ones credited with giving us the 360-degree circle.
Which we still use every day.
We do. And not just that, they divided each degree into 60 minutes of arc and each minute into 60 seconds. That whole system.
60. That feels specific.
Yeah.
Any idea why 60?
Well, one thought is maybe it's linked loosely to the number of days in a year, around 360.
Yeah.
But probably more importantly, 60 is. This is a very convenient number mathematically.
How so?
It divides evenly by so many other numbers, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. Makes calculations with fractions, especially back when you're doing it all by hand, much, much simpler.
Ah, okay. That makes practical sense. Clever.
Really quite ingenious for the time.
So they laid this groundwork. How did these early measurements, these degrees and arcseconds, actually start changing how we saw the universe?
Well, getting better and better positions, tracking things over time. That was key. It fed directly into some huge shifts, like understanding Earth's motion.
You mean figuring out we weren't the center of everything, the heliocentric model?
Exactly. That didn't happen in a vacuum. It needed data, precise observations of how planets appeared to move against the background stars. Astrometry provided that baseline.
Okay, so it helped rearrange the solar system, in our minds at least. What else?
It was crucial for figuring out the scale of the solar system too, not just the layout, but the distances involved.
Right, getting a sense of how big our cosmic neighborhood actually was.
Precisely. And then connecting that to, well, physics. Understanding the sun's motion through space, validating Newtonian physics, gravity, motion, all that. It needed accurate positional data over time.
It's like the bedrock for so much else.
It really is. And don't forget the practical side. Maritime navigation. Sailors absolutely relied on accurate star charts to find their way across oceans.
Yeah, that's a very tangible impact. Okay, so we've gone from ancient times, understanding the solar system. What was the next really big hurdle?
Distances.
Yeah.
Not just within the solar system, but to the stars themselves. That was, and honestly still is, a major driver.
Using Earth's orbit, right, looking from one side and then the other.
Yeah, parallax. Using that huge baseline, the diameter of Earth's orbit, to try and see a tiny shift in a nearby star's position against the distant background. It's a challenge people wrestled with for, well, centuries, about 400 years intensely, and we're still refining it.
And when they finally cracked it in the 1830s or so.
Oh, that changed everything.
Yeah.
Suddenly the numbers weren't just big, they were mind-boggling. It showed the sheer, almost incomprehensible vastness of space.
The universe just exploded in scale.
It really did. Those first parallax measurements revealed stars were incredibly far away, truly distant suns, and that immediately shifted the focus.
So?
It became about understanding what these stars were. Their distances, yes, but also their motions, their physical nature, how they were arranged, leading eventually to understanding the structure and dynamics, the whole life story, really, of our own Milky Way galaxy.
So measuring tiny shifts unlocked the galaxy itself.
Wow. But progress wasn't smooth sailing, was it? I remember the sources mentioned a slowdown, mid-20th century.
That's right. We hit a wall, or rather, an atmospheric layer.
Ah, the atmosphere, the reason stars twinkle.
Exactly that. That twinkling, which interestingly, even ancient Greeks like Eratosthenes noted, is caused by turbulence, particularly in the lowest bit, the troposphere, maybe the bottom 10 kilometers or so.
Air moving around different temperatures
Yeah.
messes with the light.
Precisely. It bends and refracts the starlight randomly as it passes through, like looking through, I don't know, moving water or heat haze off a road. It smears out the image.
So astronomers trying to get above it, high mountains.
That was the main strategy for a long time. Build observatories way up high where the air is thinner, drier, steadier.
Did it help much? It did, yeah. At the very best sites, you could maybe get the atmospheric blurring down to about 1 second of arc.
1 second of arc. How small is that visually?
Okay, so your eye, unaided, can maybe resolve things about 1 minute of arc apart. That's 60 times bigger. So 1 arc second is already pretty good, but
But the atmosphere set that limit.
basically, yes. For ground-based telescopes, even huge ones, while a bigger mirror gathers more light, letting you see fainter things, it doesn't magically cut through all the atmospheric turbulence better. You still hit that fundamental limit on resolution, roughly around that 1 arc second mark.
So a natural barrier. How did we eventually leapfrog that? Space, obviously, but wasn't there a step before that?
Ah, yes, absolutely crucial step, the telescope itself.
Right, early 17th century, Galileo and others.
Exactly. Credited to Dutch opticians, but Galileo really ran with it in 1609, and it brought two massive improvements.
Okay, what were they?
One, seeing much fainter things. Suddenly, the sky was filled with vastly more stars than anyone imagined.
And two.
Better resolution, better positional accuracy. The telescope's aperture allowed for much finer measurements than the naked eye ever could.
So a huge boost, but still ultimately fighting the atmosphere from the ground.
Right, which brings us to the modern era, and going above it all. Space astrometry.
Finally free of the twinkle.
Completely. And the results were, well, revolutionary. Take the Hipparcos satellite, launched back in 1989.
Okay, Hipparcos, what level did it reach?
It achieved accuracies down to 1,000th of an arc second. A milliarc second.
1,000th. Okay, that sounds ridiculously small. Can you give us a sense of what is that?
It's tough to wrap your head around. The sources give some good analogies, like seeing an astronaut standing on the moon from here on Earth,
Wow.
or spotting a golf ball in New York viewed from Europe.
Getting the idea. Tiny.
Or think about the width of a single human hair seen from, say, 10 kilometers away.
Okay, that's incredibly precise.
One more. How much your hair grows in just 1 second if you were looking at it from a meter away. That length seen from that distance.
Mind-bogglingly small angles. And then Gaia came along.
Yes, Gaia. Launched in 2013,
Oh, yeah.
taking another giant leap,
How much better?
aiming for another improvement factor of about 100 over Hipparcos. We're talking accuracies of a few microseconds of arc.
Microseconds, a millionth of an arc second. What on earth is the analogy for that?
Okay, brace yourself. This one's pretty wild. A few microseconds of arc is like distinguishing the size of a Bohr radius, the electron's orbit in a hydrogen atom, from a meter away.
I don't even know how to picture that. That's just an insane level of precision.
It truly is.
Yeah.
And the engineering needed to get there is just staggering.
I can only imagine. The optics, the detectors, keeping everything perfectly stable.
Exactly. Flawless optical quality.
Mm-hmm.
Detectors that can measure those tiny shifts, maintaining stability against tiny vibrations, temperature changes, gravitational pulls. It's a huge challenge.
Okay, so let's just pause and make sure we're clear. All this incredible tech, it boils down to measuring angles on the sky, right? Can you just recap what angular measurement means here?
Sure. Basically, we imagine the sky as a giant sphere around Earth, the celestial sphere. Astrometry pins down a star's position on that sphere using two angles.
Like latitude and longitude on Earth?
Very similar idea, yeah.
Hmm.
Two coordinates tell you where to look. Because initially, you often don't know the actual 3D distance, just the direction.
And we're still using that ancient Sumerian system. Degrees, minutes, seconds.
Amazingly, yes. That 360-degree circle, divided by 60 again, it's stuck around for over 4,000 years.
Because it was just so practical for calculations back then.
Exactly. That high divisibility of 60 was a huge advantage for manual work.
Okay, so for scale, the sun or moon in the sky, how big are they in degrees?
They both appear about half a degree across. Gives you a feel for what 1 degree looks like.
Half a degree. Okay, now 1 second of arc, you said it was useful?
Very. It's a standard unit. And visualizing it, think about something 1 meter tall.
Mm.
To make it appear only 1 arc second high, you need to view it from about 200 kilometers away.
200 kilometers.
Right. It's such a key benchmark that it actually forms the basis of the parsec, a primary unit of distance in astronomy, defined by parallax angles.
And just one more comparison for that arc second to really hammer it home.
You think of a euro coin.
Hmm.
If you looked at it from 5 kilometers away, its apparent size would be roughly 1 second of arc.
5 kilometers for a small coin. Okay, that drives home the precision involved.
It really does.
So, wrapping this up, we've journeyed from ancient eyes looking up, dividing the sky, to these unbelievably precise space telescopes. What's the big takeaway here?
I think it's really about that relentless push for accuracy. How measuring these seemingly tiny abstract angles has just completely revolutionized our cosmic perspective, again and again.
From the solar system's layout.
To the sheer scale of the universe, to understanding our own galaxy's structure, how it moves, how it formed. It all hinges on getting those positions right, more and more precisely.
It's incredible that something so technical, measuring tiny angles, could drive such fundamental shifts in knowledge.
Absolutely. And it's still ongoing. The data from missions like Gaia, it's still being analyzed, still revealing new things about stars, about the galaxy's history, even finding new planets. The quest continues.
It really makes you wonder, doesn't it? What other areas of science today, maybe things that seem really niche or technical, might be holding the keys to the next big revolutions in understanding? Something to think about.
Definitely. The story of astrometry shows that sometimes the smallest measurements can lead to the biggest discoveries.